Today we're doing section 1.8, Introduction to Linear Transformations. Another way to view AX equals B is matrix A is an object acting on vector X by multiplication to produce a new vector AX or vector B. Case 1. We have the matrix 2, 3, 1, negative 4, negative 6, negative 2. So this would be my A. My X would be 2, 3. So that's my vector X. And then that would produce a new vector B, negative 8, negative 12, 4. So like I said, this is A, X, and B. Case 2 would be when I have A here, X, and then B. Okay, so those are two cases that we would have. And what happens is we take our vector X, it's multiplied by A, and produces vector B. Suppose X is an n by n matrix. Solving AX equals B amounts to finding all X in Rn, which are transformed into B in Rn through multiplication by A. Matrix transformations. A transformation T from Rn to Rm is a rule that assigns to each vector X in Rn a vector, the transformation of X in Rm. So our terminology. Rn is the domain of T. Rm is the codomain of T. The transformation upon X in Rm is the image of X under the transformation T. The set of all images T, X is the range of T. So let's look at example 1. Let A be 1, 2, 0, 0, 1, 1. Define a transformation from R2 to R3 by Tx equals Ax if X is 2, 1. Okay, so we have Tx equaling Ax. And this would be A, would be 1, 2, 0, 0, 1, 1 times X, which is 2, 1. And just remember from when you first learned about matrices, this is a 3 by 2, and this is a 2 by 1. So our final matrix will be a 3 by 1 when we multiply this. When we multiply this, I'm just going to show the work for this. If you do this in your head, it's fine. You just need to make sure you set up this step and then give me the answer. It'd be 1 times 2 plus 0 times 1. And then 2 times 2 plus 1 times 1. And then 0 times 2 plus 1 times 1. Adding those together, I would get 2, 5, 1. So here, if I'm looking at it, this is X in R2. Okay, the domain is R2. Okay, here is my transformation upon X in R3. And this is the range. So this whole plane is the range of T. And the codomain is R3. Let's look at example 2. Let A be 1, negative 5, 2, negative 2, 10, 3, negative 15, U be 2, 3, 1, B be 2, negative 10, and C be 3, 0. Define a transformation T from R3 to R2 by T of X equals A of X. A, find X in R3 whose image under T is B. B, is there more than one X, so that should be 1, X under T whose image is B. And C, determine if C is in the range of the transformation of T. Okay, so we're going to go through this, and this one's rather lengthy. So I'm going to start with A, and what we need to do is we need to solve our transformation of X equals B for X. So we would have AX equals B. So I know that A is 1, -5, -2, 10, 3, -15, X would be X1, X2, X3, because they say R3. And B is 2, -10. So what you're going to do is you're going to have the augmented matrix, and that's how you're going to go ahead and find X. Okay, so we're going to take our augmented matrix and solve for that. And so I would have 1, -5, -2, 10, 3, 15, 2, -10. And I'm going to go straight down for this one. So what I'm going to do is I'm going to take 1/5 of this row here, because I noticed when I add it to the top row, that would cancel out, or add the top row to it, it would cancel it out. So I'm going to take 1/5 of the bottom row. So that would give me -1, 2, 3, -2. When I take 1/5 of that. And I'm actually going to take -1/5. So I'm going to make this positive and the middle 2 negative, because that will make it easier on me instead of having to subtract. So this would be negative, and that would be positive. So now what I'm going to do is I'm going to take row 2 minus row 1. And that would give me all zeros. So my system of equations would be x1 equals 2x2 minus 3x3 plus 2. x2 is free. x3 is free. So then I would have x equals 2x2 minus 3x3 plus 2, and then x2, x3. This we then could write as 2, 0, 0, because those are my constants, plus x2 times 2, 1, 0, plus x3 times -3, 0, 1. And x would be the constants, therefore x would be 2, 0, 0. And that would be your answer. So let's go ahead and look back up at B. B says, is there more than one X under T whose image is B? So let's go ahead and answer B. So is there an X for which the transformation on X equals B? So this is a uniqueness problem. So this is talking about uniqueness. So is this unique? So it's asking, is there and x for which our transformation of x equals b. And since we have two free variables, our answer would be yes, there is more than one x for which the transformation of x equals b. And then C, determine if C is in the range of the transformation of T. So this is talking about an existence problem. Is there an x for which the transformation of x equals C? So is our matrix consistent? So this is asking us, is there an x for which our transformation upon x equals C? So basically it's saying, is a times x equals C consistent? So what we would need to do is have our augmented matrix, and we would have to solve for that. So my augmented matrix for this would be 1, -5, -2, 10, 3, -15, 3, 0. And when I row reduce this, you guys can go through and do this. I'm going to give you the reduced matrix. I'd get 1, 0, -2, 0, 3, 0, 0, 1. 0 cannot equal 1, so it's inconsistent. Because a row exists in the form 0, 0, 0b. And when b cannot equal 0. Therefore, does not exist. C is not in the range of T. Linear transformations. If A is an m by n matrix, then the transformation T of x equals A of x has the following properties. T of u plus v equals A of u plus v, which is A times u plus A times v, which is the transformation of u plus the transformation of v. Plus, whenever you have a constant, you can do that. This is for all u and v and r to the n and all scalars c. Let's go ahead and look at this one. Example 3, let E1 be 1, 0, E2 be 0, 1, Y1 be 1, 0, 2, Y2 be 0, 1, 1. Suppose T, a transformation from R2 to R3, is a linear transformation which maps E1 into Y1 and E2 into Y2. Find the images of 3, 1, or 3, 2, and X1, X2. So our first step is, if I'm looking at these down here, this right here is E1. This right here is E2. Okay, so that's what we have in there. When I look first, what we want to do is our transformation of E1 equals Y1. And our transformation of E2 equals Y2. Step 2, this transformation, 3E1 plus 2E2 would equal 3,2. So that's step 2. And then step 3, and so if I look down here, this is 3E1 plus 2E2. And here I have my transformation of E1, my transformation of E2, and this would be my transformation up here of 3E1 plus 2E2. So my step 3 would be the transformation of that. So this would be the transformation of 3E1 plus 2E2, which then we know we can write, factor out that those constants, those scalars. And we know that E1 transforms to Y1 because that's what they're mapping it onto. So this would be 3Y1 plus 2Y2 because E2 maps into Y2. And then 3, we know that Y1 is 1, 0, 2, and Y2 is 0, 1, 1. This then would be 3, 0, 6 plus 0, 2, 2, which would then equal 3, 2, 8. Which, if you look, that would be 3, 2, 8. Example 4. Define our transformation from R3 to R2 such that the transformation of x1, x2, x3 equals the absolute value of x1 plus x3 and 2 plus 5x2. Show that t is not a linear transformation. So this is just another way to write a transformation. So another way to write a transformation, I could have my transformation of x1, x2, x3, and they're saying it transforms to the absolute value of x1 plus x3 and 2 plus 5x2. So what we need to do is show that t is not a linear transformation. So one way that we could do this is we could provide a counterexample. So where our transformation of 0 equals 0, our transformation of CU equals CT, C times our transformation of U or our transformation of u plus v equals our transformation of u plus our transformation of v. So here's my counterexample. So my transformation of 0 would be a transformation of 0, 0, 0 equals 0, 2, which does not equal 0, which means t is not linear.